Welcome to the deep dive. In the machine learning and data science communities right now, the recent triumphs of these large reasoning models are pretty much universally attributed to chain of thought.
Right, yeah. It's the big narrative.
Exactly. We see frontier models outputting these specific, like, aha tokens or generating paragraphs of deliberation, and we just assume they're methodically working through a problem.
Yeah, we look at that human interpretable reasoning process and we assume it's a transparent window into the actual computation.
But what if that is entirely an illusion?
I mean, it is arguably the most critical question in AI architecture today. When a model says, let me think about this, are we witnessing algorithmic deliberation? Or are we simply projecting human cognitive processes onto a highly optimized matrix multiplication?
And that is exactly our mission for this deep dive. To answer that question, we're analyzing a really fascinating preprint titled Beyond Semantics, the Unreasonable Effectiveness of Reasonless Intermediate Tokens.
Yeah, it's a paper out of Arizona State University.
Right, ASU. And our goal today is to systematically unpack their highly controlled experiments on transformer models to determine whether the actual semantic meaning of derivational traces influences model performance at all.
And, just to set the paradigm for you, the listener,
Mm-hmm.
we are keeping this strictly focused on the empirical findings, the methodology, and the technical novelty of this paper.
No wild speculation.
Exactly, no wild speculation. We are looking at the raw data. The authors set up this brilliant model organism to test chain of thought.
By doing this, they deliberately bypass the opaque proprietary nature of frontier models, allowing us to examine a fully transparent, verifiable system. Okay, let's unpack this.
Let's do it.
In the wild, natural language chain of thought is fundamentally polysemantic. For you tuning in, that means the tokens carry multiple overlapping meanings simultaneously.
Right.
So if a model like, say, DeepSeek's R1 outputs 3 pages of meandering text, you can read almost any intent or logical structure into it. So how did the researchers bypass that ambiguity to actually measure what we could strictly define as reasoning?
Well, to appreciate their main contributions, we first have to recognize why testing chain of thought using natural language is fundamentally flawed for rigorous structural analysis.
Okay, why is that?
Because in domains like math or general question answering, natural language traces simply lack a formal ground truth.
Ah, right.
You cannot definitively prove the model utilized the logic it claims to have used in its output. That leads to these incredibly noisy faithfulness evaluations where, you end up relying on another LLM to judge the reasoning.
Which just compounds the error.
Exactly. It's turtles all the way down.
So they just threw out natural language entirely.
They did. They trained 0.5 billion parameter Quinn 2.5 decoder-only models entirely from scratch.
And they reduced the parameter count down to roughly 380 million, right? Using custom tokenization to scope it strictly for their controlled environment.
Yeah, they restricted the vocabulary to exactly 944 tokens. And the task they chose was shortest path planning in 30 by 30 grid-based mazes.
But they didn't just train the models on the final solved paths.
No. They trained them on the exact linearized execution traces of the A-star search algorithm.
Okay, let me make sure the mechanics of that are clear for the audience. We are talking about the formal algorithmic state at every single step of the computation.
Right, the absolute exact state.
So the training traces included the exact additions to the open and closed lists. They included the specific grid coordinates being evaluated and the precise G and H cost values.
And for the H value, the heuristic estimating the distance to the goal, they utilized a Manhattan distance calculation.
Meaning it only allowed orthogonal movements, no diagonals.
Exactly. That level of granularity is crucial. And to rigorously test both in-distribution and out-of-distribution generalization, they exposed the models to highly diverse maze generation algorithms.
So for acyclic trees mazes without any loops, they used Wilson's and Kruskal's algorithms.
Right, and they also used randomized depth-first search to generate mazes that are heavily biased toward long, winding corridors with low branching factors.
And then they introduced the really difficult topologies for ode testing. They used Drunkard's walk and what they call search former style generation.
Yeah, those methods permit loops, which creates incredibly noisy, cyclic, cave-like structures that look completely different from the tree-based mazes.
Okay, so once they had this rigorous environment, they needed a way to measure if the transformer was actually reasoning.
Right, and to do that, they built a formal A-star validator. And I want to be clear, this isn't a prompt asking an LLM if the output looks correct.
Right, it's deterministic.
Exactly. It's a deterministic Python script that parses every single generated trace to check for strict algorithmic adherence.
It catches parsing errors, flags invalid neighbor expansions like if the model tries to mathematically move through a wall or jump across the board, and it catches premature closures.
Or referencing nodes that are not currently in the open list.
If I can jump in with an analogy aimed right at the software engineers listening, think of this setup like unit testing a discrete algorithm. We are forcing the transformer to output the exact state of an A-star priority queue at every single step.
Yeah, that's a great way to think about it.
Logically, shouldn't the network just inductively learn the underlying formal algorithm from all that perfect training data?
Well, that is the baseline intuition most practitioners operate under.
Yeah.
If the model is outputting the perfect, flawless syntax of A-star, it must have learned the underlying mechanics of A-star.
Right.
But that assumption leads directly into the first major empirical shock of the paper. We see a massive, inexplicable divergence between the correctness of the final plan and the validity of the intermediate trace.
Let's look at the baseline results, because this is where the unit test conceptually fails. The authors found that models trained on completely correct A-star traces can frequently produce the correct final solution while generating completely invalid intermediate reasoning traces to get there.
The data paints a very strange picture. Take the model trained strictly on the Wilson-generated mazes. It achieved a 79.9% plan accuracy on its in-distribution test set.
Okay, pretty good.
But when the authors isolated only those correct plans and checked the trace validity, it was 97.7%.
Meaning 2.3% of the time, the model hallucinated an impossible mathematical step in its intermediate reasoning, but still arrived at the perfect final answer.
Exactly.
Now, I know 97.7% sounds high, but if the trace is semantically driving the solution, it should logically be 100%. A broken algorithm shouldn't yield a perfect result.
And the gap widens significantly when we look at the model trained on the search former style data.
Right.
That model achieved a 40.8% plan accuracy, but the trace validity for those successful plans was only 89%.
Wow. So the model is arriving at the destination, but the map it is drawing to get there has literal impossibilities on it.
Yeah, and they stress this system even further with a length generalization experiment. They binned the A-star problem difficulty by token length, testing the model on traces going all the way up to 4,500 tokens.
Because they wanted to observe the network's behavior when pushed owed purely by computational difficulty.
Right. As the trace length increased, overall plan accuracy naturally plummeted. But the critical finding is what happened to the trace validity among the remaining correct solutions.
This is the crazy part.
In the hardest bin problems requiring 4,000 to 4,500 tokens, the trace validity for correct plans dropped to 51.8%.
So what does this all mean? We have a scenario where half the time the model is arriving at the mathematically optimal path, its intermediate search steps are mathematically invalid. What is the trace actually doing? Is the meaning of the trace entirely irrelevant?
Synthesizing what this means mathematically for ML practitioners requires a fundamental shift in perspective. The model is internalizing the style, the syntax, and the cadence of the A-star algorithm without ever acquiring its underlying mechanistic logic.
It's mimicking the form of computation.
Exactly, it's mimicking it. The correlation we observe between trace validity and solution correctness is merely an artifact of the training distribution. It is not a fundamental property of the transformer's problem-solving process.
Which sets up the exact question the authors asked next. And this leads to the paper's most novel and, frankly, counterintuitive contribution.
It really is.
If valid traces are not strictly necessary for high performance, what happens if we actively destroy the semantic meaning of the training data?
This is where they introduced the swapped trace experiments. They took their original data set of 500,000 training problems, and during the supervised fine-tuning phase, the phase where you teach the model how to respond to prompts, they randomly permuted the intermediate A-star traces.
I want to make sure the mechanics of this permutation are crystal clear. They took a maze problem. Let's call it maze A.
Okay.
They paired it with a structurally valid A-star execution trace, but a trace that belonged to a completely different, unrelated maze. Let's say maze Z. And then they appended the correct final plan for maze A at the very end of that sequence.
Exactly. So the trace is algorithmically valid in a vacuum, but semantically, it is utter garbage relative to the specific problem the model is being asked to solve.
And the main finding here completely upends conventional wisdom. The models trained on these corrupted, entirely irrelevant traces performed comparably to and frequently better than the models trained on correct semantically aligned traces.
The out-of-distribution breakthrough is particularly revealing here. Let's look at the models trained on the search former style data. The normal model achieved a 62.1% plan accuracy when tested on the highly cyclic Drunkard's Walk mazes.
Okay, 62.1.
But the model trained on the swapped, irrelevant traces achieved an astonishing 95.4% plan accuracy on that same out-of-distribution dataset.
It obliterated the normal model. And unsurprisingly, because it was trained on disconnected data, the trace validity for the swapped models was a flat 0% across the board.
They never output a valid reasoning trace, yet they solved the problem vastly better. And to prove this wasn't just a localized anomaly, the authors ran an interpolation experiment.
Where they gradually increased the percentage of swapped traces in the training data from 0% up to 100% and mapped the performance.
Right. They found a fascinating U-shaped performance curve.
Yeah, introducing a small amount of trace swapping, say 25 or 50%, actually hurts plan accuracy. The model gets confused by the conflicting signals.
But as you push past that, moving toward 100% swap data, the plan accuracy rises again, eventually matching or beating the baseline.
I have to admit, I struggled to wrap my head around this. Giving the model literal problem irrelevant garbage for its chain of thought makes it better at generalizing to unseen maze topologies.
I know, it sounds absurd.
It completely shatters the anthropomorphic idea that the model is deliberating over the maze. I really have to push back on the prevailing narrative here. If the model isn't using the trace to think, why does outputting the irrelevant trace help at all compared to just forcing the model to output the final answer immediately?
Well, the answer lies in how transformers actually process information. This proves that intermediate tokens improve accuracy, not because they impart human interpretable semantic algorithms.
Then why?
They help because they provide a consistent structural computation pad.
A computation pad, like a buffer.
Precisely. The sheer volume of tokens acts as a buffer. Every token generated allows the transformer another forward pass, another layer of computational depth to process the initial prompt's hidden states before being forced to output the final answer.
So the trace acts as a metronome for computation, not a map of the logic.
Exactly.
If I can offer an analogy, imagine I hand you a complex calculus problem. If I force you to solve it instantly in your head, you might fail.
I definitely would.
Right. But if I give you a piece of scratchpad paper and you just start drawing random spirals and squiggles on it for 5 minutes while holding the initial calculus problem in your working memory, you eventually output the correct answer.
The squiggles didn't solve the math.
Exactly. But the act of drawing them gave your brain the time and structural space to process the problem in the background.
That is a highly accurate way to visualize it. The supervised fine-tuning data is merely teaching the model the syntax of the squiggles, what kind of shapes to draw on the scratchpad. It is not teaching the logic of the solution.
Okay, supervised fine-tuning is one thing. But having demolished the necessity of semantics in that phase, we have to address the other massive pillar of current reasoning models, reinforcement learning.
Yes, specifically GRPO.
Right, group relative policy optimization. This is the mechanism that community assumes is responsible for the deep computational effort we see in frontier models.
Those aha moments that made models like DeepSeek's R1 famous emerged heavily during RL post-training. So the authors applied GRPO to their maze models.
And with GRPO, you evaluate a group of outputs and reward the model purely for producing the correct final plan, regardless of what the intermediate trace looked like.
They optimized purely for the destination, ignoring the map. And applying GRPO drastically improved final solution accuracy across all distributions, which perfectly aligns with what we see in the industry.
However, the critical observation is that this massive accuracy boost did not enhance trace validity.
Not at all. For the normal search former style models, applying GRPO steadily degraded trace validity. It dropped from the mid-80s down to the mid-50s, while plan accuracy soared.
The RL optimization process actively discarded semantic correctness because it wasn't strictly necessary for finding the optimal path. The model learned that faking the math was more efficient than doing the math as long as it got the right answer.
Yeah, and the swapped models, the ones trained on irrelevant traces. They maintained their flat 0% trace validity, but continued to completely dominate in solution accuracy after RL.
Which dismantles another major assumption, the myth of inference-time scaling. The prevailing narrative in the ML community suggests that when a model generates a longer chain of thought, it is dynamically recognizing a harder problem and adaptively allocating more compute to solve it.
It's supposedly thinking harder.
Right. To test that, the authors plotted the generated model trace lengths against the ground truth A-star trace lengths, the ground truth length being the objective computational complexity of the maze.
And the scatter plots revealed absolutely no correlation. The data is highly dispersed. If the model were truly problem adaptive, you would see the data points cluster tightly along a diagonal line. Harder problem equals longer trace.
But they don't?
No. Instead, especially in out-of-distribution settings, the generated trace lengths fluctuate wildly and completely independently of the problem's complexity.
The paper noted that very often the model simply babbles intermediate tokens, hitting the 32,000 maximum context limit without ever actually solving the maze. It's just spinning its wheels.
The length of a trace is largely agnostic to underlying computational complexity. It is an artifact of sampling behavior and the training distribution, not genuine problem-adaptive computation.
Here's where it gets really interesting regarding the broader conversations happening in the industry right now. There's a lot of fear surrounding AI safety narrative.
Oh, definitely.
People worry about models showing deceptive thoughts in their chain of thought or hiding their true intentions in these intermediate steps. But if these traces don't actually mean anything mathematically, if they are just structural artifacts of the sampling behavior,
then those safety fears might be massively overinterpreting meaningless tokens. We are taking a computational buffer, the scratch pad filled with squiggles, and we are applying human psychopathology to it.
we are assuming intent where there is only a learn a syntactical cadence. So let's bring all these threads together. We have a situation where supervised fine-tuning on correct traces isn't actually teaching the algorithm. We know swapped, irrelevant traces perform better ODE. We see that RL degrades trace validity while boosting accuracy. And we know trace length has no correlation to problem difficulty.
Right.
What is the author's ultimate theoretical takeaway regarding what intermediate tokens are actually doing?
The core innovation of this paper is isolating the mechanism. The effectiveness of chain of thought does not arise from human interpretable semantics. Instead, the authors speculate that intermediate tokens act as a prompt augmentation. Mathematically, they represent a learned Skolem function.
I want to make sure we define that clearly for the listener. In mathematical logic, a Skolem function replaces an existential variable with a specific function that guarantees a valid output. How does that map to what the transformer is doing?
Well, in this context, it means the network learns a function that takes the specific task prompt, in this case the maze, and maps it to an effective, though entirely uninterpretable augmentation. This augmentation simply shifts the probability distribution in the latent space toward generating the correct final solution.
It is essentially discovering a latent space hack that makes the final answer mathematically inevitable.
Yes.
And the authors draw a brilliant parallel to adversarial prompting. We've seen in jailbreak literature that inserting uninterpretable gibberish or specific noise sequences into a prompt can dramatically alter a model's output, bypassing safety guardrails.
Right. And chain of thought might just be the model generating its own beneficial gibberish to bypass its own predictive limitations.
It uses the intermediate tokens to manipulate its own internal state space into a more favorable geometry for decoding the final answer?
Exactly. The fact that this geometric manipulation happens to look like English, or looks like A-star execution code, is just a byproduct of the data it was exposed to during training. It is not a requirement for the computation itself.
Which leaves us with a truly profound, forward-looking question for you to mull over. If human interpretable reasoning traces are just an anthropomorphic illusion, a comfortable fiction that isn't mathematically necessary for high performance, what happens when we stop forcing models to think in English?
That's the billion-dollar question. If future reasoning models are allowed to develop entirely alien, continuous, latent space thoughts, optimized purely for accuracy rather than human readability, they will likely become vastly more efficient and capable.
But we will lose our only window into their computational process.
We will be staring at a debug log that isn't just hallucinated, but fundamentally encrypted in an alien geometry.
We built these models wanting an X-ray of the engine, but we might just have to accept that the most efficient way for the engine to run is in total darkness.
Well said.
That is all the time we have for our exploration of this preprint. We appreciate you joining us for the deep dive, and we highly recommend checking out the original paper, Beyond Semantics, by the team at ASU for the full mathematical breakdowns. Keep questioning the logs.